In our last video, we talked about fatty acids, and this overview page shows us 6 different fatty acids that I'd like you to be familiar with. We talked about palmitic acid and oleic acid, or oleate and palmitate, and some of these are saturated and some of them are unsaturated. Notice these are all part of our polar lipids or amphipathic lipids. These have a very charged polar head and a long nonpolar tail. I pointed out that these are the fuel that we use for long-term energy storage in our body, but that's actually not quite true. In fact, what we're going to do is learn about how we take these fatty acids and package them into the form that's the true storage form for that energy in our body, and that's going to be triacylglycerols down here. Notice we're going from amphipathic and polar to all non-polar molecules, and we're going to see how that's really important as we move ahead. Okay, so let's go to the next page, and we are going to talk on this page mainly about triacylglycerols. I sometimes just call these TAG for short, and you'll see me do that a lot. Now, in order to form triacylglycerols, we've got to understand a new type of linkage. Remember, we've done this before. We looked at how amino acids come together with peptide bonds to make proteins. We talked about how sugars come together with glycosidic bonds to make polysaccharides. This is our next linkage, and it's a really important one. Okay, what we're going to do is we're going to draw out a fatty acid right here. And I'll just go ahead and make it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's good enough for now. It can be any length, any number of double bonds. We're going to bring that fatty acid close to a molecule we call glycerol. Now, I introduced this compound, glycerol, in our sugar chapter. It's not a sugar. It's actually a reduced form of a sugar. We take the glyceraldehyde triose and take the aldehyde and make it into an alcohol by reduction. Now, we're going to do something we've done many times before. We're going to take a water and get rid of it. It's a dehydration type process, and we're going to connect what is left over. And when we do so, we create a whole new linkage, and that's called an ester. Now, we learned esters before as a functional group. Remember, CO bridged to another C, double bond O. That is not only a functional group, but it's also a linkage. Just like peptide bonds and amides are linkages and functional groups at the same time. Now, we can do this 3 times. I'm just going to write right over that as if we're adding in another fatty acid. Again, it doesn't matter how many we have. Maybe we'll throw a double bond in there just like that, whatever. We'll do it a 3rd time. Maybe we'll have just another saturated fatty acid here. But again, I just want to point out COC double bond O, COC double bond O. These are all esters. Now, we can understand where the tri comes from because we've got 3 fatty acids attached to glycerol. But what about this last part? What about the acyl? What does that mean? Well, acyl is simply when you have some kind of a carboxylic acid attached to something else. After all, these are no longer fatty acids. They're no longer carboxylic acids. They're embedded or linked into an ester. So in that case, we call them acyl groups. So this is 3 acyl groups attached to a glycerol. So let me make sure you understand this. That water is really gone. We took it away when we did this reaction. There's no bond there either. Now we have a whole new molecule, and let's make a couple of notes about it. First of all, when we took these amphipathic fatty acids with charged head groups, we would expect them to have O- on those carboxylates, and we cap it with a glycerol, we've made a nonpolar cap. So now, instead of an amphipathic molecules, we have nonpolar tails and a nonpolar cap. This is a slightly polar region, but it's not enough. This triacylglycerol is a fully nonpolar molecule, very much insoluble in water. Oh, by the way, one thing that gets people mixed up sometimes is, let me make sure you understand, this portion right here is the glycerol, not the whole thing. The whole thing is a triacylglycerol. The backbone only is glycerol there. So we're going to look over here now and show you this little cartoon version that we put together to show you how these triacylglycerols are assembled. We have a glycerol backbone and 3 fatty acids like that. Now we have little tiny connectors here, and those look kind of fragile, and that's on purpose because we still have 3 pieces or parts that we're putting together, the 3 fatty acids here and the glycerol. The ester linkages right here are somewhat fragile in the sense that we can make them and we can use a water to break them. So we can put these pieces together and we can take them apart, and we'll do that later as we move on. Let me make sure that you understand. These are ester linkages right there. Let's get our notes complete in that way. Okay, we've got a couple of minutes to go. Let's point out that these triacylglycerols are the long-term storage of energy. And what that means is it's going to be true in animals like us or like cows and pigs, that we have animal fats. So think about bacon and bacon grease or the bacon fat. That is going to be a triacylglycerol. But it's also true that vegetable oils, think about corn oil or olive oil, things like that, that's the same type of molecule. So what's the difference? The difference is that these, one is liquid, obviously, and the other is solid at room temperature. Let's pause for a second and see if you can predict which one of these has more double bonds and which one has fewer double bonds. That's going to be based on something we talked about, how those double bonds cause kinks in the fatty acids. See if you can make that prediction, and then we'll circle around and go through it. Okay, hopefully you had a chance to think about this, and the answer is as follows. If you have a vegetable oil that's liquid, it is a liquid because it has more double bond. That is, it's got a lot of unsaturation in it. That unsaturation, those double bonds, make kinks, and those kinks prevent the fatty acids and the triacylglycerols from packing together well, and that means it takes less heat to make them into a liquid. Animal fats, we can't say that they don't have double bonds. They have fewer double bonds, and that makes these straighter, and therefore they pack together a little bit better. So that's kind of an interesting little connection to food science and nutrition. We may know that animal fats are worse for you because they have saturated fats, which are supposed to be worse for us. And vegetable oils are better for us because they have polyunsaturated fatty acids. So that's something you might connect with in another class. Let me finish with one last thing on this page. Why is it that we take these beautiful fuel molecules, these fatty acids, and put a nonpolar cap on it? We got to understand, if we have amphipathic molecules and we put them in water, they form micelles. Maybe you remember that. And that's not a great way to store things. But if we put a cap on there that's nonpolar, they can be stored in the absence of water. Stored without water. I mean, think about it. Think about vegetable oil. If you put that in water, it gloms together. It doesn't want any water around. In fact, it'll exclude water. So if we're going to carry energy around for a whole season, I mean, think of a bear that builds up its fat reserves for hibernation. The bear doesn't want to carry around a lot of extra water. That is no good for energy storage. That's just extra weight. We can pack together a lot of fat or a lot of oil, and that's very high density because it's pure energy without water. Great. That's the end of this one about triacylglycerols, and we'll move on to our next video.